Hello friends, in this video we will discuss permutation group. So for that first we define order of a group. So let G with star be a finite group, then the number of distinct elements in G is called the order of a group G. It is denoted by O of G or cardinality of G. For example, let G is equal to 1i minus 1 minus I. Here G has 4 distinct elements, then order of G is equal to 4. Second example, order of Zn is equal to n. Why? Zn is equal to 0, 1, 2 and so on n minus 1. So Zn has n distinct elements. Therefore, order of Zn is equal to n. Now we define permutation. So let S be a finite set having n distinct elements, then a 1-1 mapping from S onto S is called a permutation of S and it is of degree n. Now some remarks. So first remark, let S is equal to A1, A2 up to An means S has n distinct elements. Then permutation F is defined as A1, A2 up to An, A1 goes to B1, A2 goes to B2 and so on, An goes to Bn. Here F is function from S to S and it is defined as f of ai is equal to bi for all bi from S. Here a1 goes to b1 means f of a1 is equal to b1. Here a2 goes to b2 means value of f at a2 is b2. Similarly, we can write f of an is bn. Therefore, f of ai is equal to bi for all bi from S. Now, second remark, if S is equal to 1, 2 means 2 elements, then set of all permutations on S is called S2 and is defined as first element is P1 means permutation 1 which is called identity element is same as 1 goes to 1 and 2 goes to 2. Now second element is called permutation 2 means P2 is defined as 1 goes to 2 and 2 goes to 1. Simply it is written in cycle form 1 2 means 1 goes to 2 and 2 goes to 1. Now third remark, if Sn be the set consisting of all permutation of degree n, then Sn will have n factorial distinct elements. That is, order of Sn is equal to n factorial. Here S has 2 elements implies S2 has 2 factorial which is 2 elements. Now fourth remark, Sn is equal to f where f is a permutation of degree n is forms a group under composition of function and which is called a symmetric group. Now we define identity permutation. If I is a permutation of degree n such that I of A is equal to A for all A belongs to S, then I is called the identity permutation of degree n. For example, let S is equal to 1, 2, 3 up to n means n elements, then identity permutation is I is defined as 1, 2, 3 up to n. 1 goes to 1, 2 goes to 2, 3 goes to 3, n goes to n is equal to, it is also written in cycle form as 1 goes to 1, 2 goes to 2, 3 goes to 3 and so on, n goes to n. So it is called an identity permutation on S of degree n. Now we define equality of two permutations. So let S be any finite set, then two permutation f and g of degree n on S are said to be equal If we have f of a is equal to g of a, this condition is held for all a from S. Means value of f at any point a is same as value of g at that point. For example, if S is equal to 1, 2, 3, 4 and F is defined as 1, 2, 3, 4, 1 goes to 2, 2 goes to 3, 3 goes to 4, then 4 goes to 1. It is also written in cycle form as 1, 2, 3, 4 means 1 goes to 2, 2 goes to 3, 3 goes to 4, then 4 goes to 1. And G is defined as 2, 4, 3, 1. 2 goes to 3, 4 goes to 1, 3 goes to 4 and 1 goes to 2 means it is also written in cycle form 1 goes to 2, 2 goes to 3, 3 goes to 4 then 4 goes to 1 means 1, 2, 3, 4. So F and G are two permutation of degree 4, then we have F is equal to G because value of f at any point is same as value of g at that point. Now some more remarks on permutation. So if S is equal to 1 to 3, here S has 3 elements, then the set S3 of all permutations of degree 3 will have 3 factorial is equal to 6 distinct elements. Now we find elements of S3. So first element which is called first permutation P1 is equal to defined as 1 goes to 1, 2 goes to 2, 3 goes to 3 means identity permutation. Simply we denote by I. Second permutation called P2 is defined as 1 goes to 2, 2 goes to 1 and 3 goes to 3. It is written as simply 1 goes to 2 and 2 goes to 1. No need to write 3 goes to 3. Now third permutation which is defined as 1 goes to 3, 3 goes to 1 and 2 goes to 2. So here we write in cycle form 1 goes to 3 and 3 goes to 1. No need to write 2 goes to 2. Now permutation for 1 goes to 1, 2 goes to 3 and 3 goes to 2. So simply we write cycle form 2 goes to 3 and 3 goes to 2. No need to write 1 goes to 1. Now fifth permutation called P5 is same as 1 goes to 2, 2 goes to 3 and 3 goes to 1. So it is written as 1, 2, 3. Now sixth permutation 1 goes to 3, 3 goes to 2 and 2 goes to 1. So it is written as 1, 3, 2 in cycle form. So this all are elements of S3. S3 has 6 elements. Now we discuss about how we find product or composition of two permutation. So the product or composition of two permutations F and G of degree n, it is denoted by F composition G and is obtained by first carrying out the operation defined by F and then by G. For example, suppose Sn is the set of all permutations of degree n. Let F is defined as B1 goes to C1, B2 goes to C2 and Bn goes to Cn, and G is defined as A1 goes to B1, A2 goes to B2 and so on, An goes to Bn, B2 elements of Sn. Now we define product of F and G, or we write F composition G, which is same as this is value of F and this is value of G. Now we define F for G. So first we write elements of G, A1, A2 up to An. Now A1 goes to B1 in G. Now we show B1 goes to C1. So finally A1 goes to C1 via B1. So in composition we write A1 goes to C1. Now A2 goes to B2, then B2 goes to C2. So in composition we write A2 goes to C2 via B2 and so on. An goes to Bn and Bn goes to Cn. So finally An goes to Cn. So this is also element of Sn. So That's why we define permutation first. Now we see some examples on permutation group. So first example, let sigma is defined as 1, 2, 3, 4, 5, 6. 1 goes to 3, 2 goes to 1, 3 goes to 5, 4 goes to 4, 5 goes to 6, 6 goes to 2. It is also written in cycle form that 1 goes to 3, 3 goes to 5, 5 goes to 6, 6 goes to 2, then 2 goes to 1. So it is written as 1, 3, 5, 6, 2. 4 goes to 4. So no need to write 4. And tau is defined as 1, 2, 3, 4, 5, 6. 1 goes to 5. 2 goes to 3. 3 goes to 1. 4 goes to 6. 5 goes to 2. And 6 goes to 4. So it is also written in cycle form that 1 goes to 5. Then 5 goes to 2. Then 2 goes to 3. Then 3 goes to 1. So it is written as 1, 5, 2, 3. Now 4 goes to 6 and 6 goes to 4. So it is written in second cycle. So 4 goes to 6. Now we have to find tau or sigma, sigma or tau, sigma square and sigma inverse. So solution. So first tau or sigma means tau and sigma. So this is tau and this is sigma. Now we take composition of tau with sigma. So here first we write elements of sigma means 1, 2, 3, 4, 5, 6. Here 1 goes to 3, then 3 goes to 1 means 1 goes to 1. Now 2 goes to 1 and 1 goes to 5. So finally 2 goes to 5. 3 goes to 5, then 5 goes to 2 means 3 goes to 2. 4 goes to 4 and 4 goes to 6. So here 4 goes to 6. Now 5 goes to 6, then 6 goes to 4. So 5 goes to 4. 6 goes to 2, then 2 goes to 3 means 6 goes to 3. So this is composition of tau with sigma. Now this element is also written in cycle form that 1 goes to 1 means no need to write 1 goes to 1. 2 goes to 5, 5 goes to 4, 4 goes to 6, 6 goes to 3, then 3 goes to 2 means it is written as 2, 5, 4, 6, 3. Means 2 goes to 5, 5 goes to 4, 4 goes to 6, 6 goes to 3, then 3 goes to 2. Now we find second sigma of tau means sigma of tau. So first sigma element, then tau element. Now we write first element of tau means 1, 2, 3, 4, 5, 6. Now here 1 goes to 5, then 5 goes to 6. So 1 goes to 6. 2 goes to 3, then 3 goes to 5. So 2 goes to 5. 3 goes to 1, then 1 goes to 3. So 3 goes to 3. Now 4 goes to 6, then 6 goes to 2. So 4 goes to 2. 5 goes to 2, then 2 goes to 1. So 5 goes to 1. 6 goes to 4 and 4 goes to 4. So 6 goes to 4. So this is element sigma or tau. So it is also written in cycle form. Here 1 goes to 6, then 6 goes to 4, then 4 goes to 2, then 2 goes to 5 and 5 goes to 1. So it is written as 1, 6, 4 to 5. Now remaining element is 3 and 3 goes to 3. So no need to write 3. Now we find value of sigma square. So sigma square is nothing but sigma of sigma. Now value of sigma is 13562. So sigma of sigma is 13562 of 13562. Now we find composition of these two functions. So here 1 goes to 3, then 3 goes to 5 means 1 goes to 5. Now we find element after 5. So here 5 goes to 6, 6 goes to 2, so 5 goes to 2. Now we find element after 2. So here 2 goes to 1, then 1 goes to 3. So here 2 goes to 3. Now we find element after 3. Here 3 goes to 5 and 5 goes to 6. So 3 goes to 6. Now we find element after 6. Here 6 goes to 2 and then 2 goes to 1. So 6 goes to 1. So this cycle is over. Now remaining element is 4. So here 4 goes to 4 by default. Here also 4 goes to 4. So 4 goes to 4. So no need to write 4. Now we find value of sigma inverse. So sigma inverse is nothing but this is sigma and inverse. Now here 1 goes to 3. So in sigma inverse we write 3 goes to 1. Here 2 goes to 1. So in sigma inverse we write 1 goes to 2. Here 3 goes to 5. So in sigma inverse we write 5 goes to 3. Here 4 goes to 4. So in sigma inverse we also write 4 goes to 4. Here 5 goes to 6. So we write 6 goes to 5. Here 6 goes to 2. So here we write 2 goes to 6. So this is value of sigma inverse. This value is also written in cycle form as 1 goes to 2, 2 goes to 6, 6 goes to 5, 5 goes to 3, then 3 goes to 1. So 1, 2, 6, 5, 3 and 4 goes to 4 itself. So no need to write 4 goes to 4. Now example 2. So question is let f is equal to 1, 2, 3 of 1, 4, 5. This is element of S5. Then you have to find f inverse and f raised to 99. So solution of this question is here f is 1, 2, 3 of 1, 4, 5. So 1 goes to 4, then 4 goes to 4. So 1 goes to 4. Now 4 goes to 5, then 5 goes to 5. So 4 goes to 5. 5 goes to 1, then 1 goes to 2. So 5 goes to 2. Here 2 goes to 2, then 2 goes to 3. So 2 goes to 3. Here 3 goes to 3, then 3 goes to 1. So 3 goes to 1. So this is element f 1, 4, 5, 2, 3. Now we find f square, which is f of f, means f is 1, 4, 5, 2, 3 of 1, 4, 5, 2, 3, which is same as 1, 5, 3, 4, 2. Because 1 goes to 4, then 4 goes to 5. So 1 goes to 5. Similarly, we get 3, 4 and 2. Now we find f cube. F cube is nothing but f square of f. Here f square means 1, 5, 3, 4, 2 and f is 1, 4, 5, 2, 3. Now composition of these two functions, we will get 1, 2, 4, 3, 5. Now we find f raised to 4, which is f square of f square. So this is f square 1, 5, 3, 4, 2. So 1, 5, 3, 4, 2 of 1, 5, 3, 4, 2. Then we get 1, 3, 2, 5, 4. Now f raised to 5. So which is same as f raised to 4 of f. So this is f raised to 4. 1, 3, 2, 5, 4. Then f is 1, 5, 1, 4, 5, 2, 3. Now here 1 goes to 4, then 4 goes to 1, means 1 goes to 1, cycle over. Now 2 goes to 3, then 3 goes to 2, so 2 goes to 2, cycle over. 3 goes to 1, then 1 goes to 3, means 3 goes to 3. 4 goes to 5, then 5 goes to 4, so 4 goes to 4. 5 goes to 2, then 2 goes to 5, so 5 goes to 5. So this is an identity element. So here we get f raised to 5, which is nothing but f raised to 4 of f, and this is an identity element, means f inverse is f raised to 4, because composition of these two function is identity element. Therefore these two are inverse of each other. So f inverse is nothing but f raised to 4, and which is 1, 3, 2, 5, 4. Now f raised to 99, which is same as f raised to 95 plus 4, which is same as f raised to 5 into 19 plus 4, which is same as f raised to 5 raised to 90 of f raised to 4. Now we know that f raised to 5 is identity element. So here f raised to 5 is I. So I raised to 19, which is identity element. Now identity element composite with f raised to 4, then we get f raised to 4 itself. So we get f raised to 99 is 13254. Now third example. So question is, show that S3, the set of all permutations on three symbols 1, 2 and 3 is a finite non-abelian group of order 6 with respect to composition of function. So we have to show that S3 is group with respect to composition of function. So solution of this question. So we know that we also discuss in theory part that S3 is equal to identity element 1 2 1 3 2 3 1 2 3 then 1 3 2. Now this example prove by using composition table. So this is composition table. Now here we write composition sign. Now these are the elements of S3. Now first element I of I means we get identity element, then I of 1 2, then we get 1 2 itself, I of 1 3, then we get 1 3. Similarly, we get 2 3, 1 2 3, and 1 3 2. Now we find 1 2 of identity element, then we get 1 2 itself. Now 1 2 compose with 1 2, then we get identity element, then 1 2 composite with 1 3, then we get 1 3 2. 1 2 compose with 2 3, then we get 1 2 3. 1 2 of 1 2 3 we get 2 3. 1 2 of 1 3 2 we get 1 3. Now 1 3 of I we get 1 3. 1 3 of 1 2 we get 1 2 3. Now 1 3 of 1 3 we get identity element. Then 1 3 of 2 3 we get 1 3 2. Now 1 3 of 1 2 3 we get 1 2. 1 3 of 1 3 2 we get 2 3. Now 2 3 of identity element we get 2 3 itself. 2 3 of 1 2 we get 1 3 2. 2 3 of 1 3 we get 1 2 3. Now 2 3 of 2 3 we get identity element. 2 3 of 1 2 3 we get 1 3. 2 3 of 1 3 2 we get 1 2. Now 1 2 3 of I we get 1 2 3 itself. 1 2 3 of 1 2 we get 1 3. 1 2 3 of 1 3 we get 2 3. 1 2 3 of 2 3 we get 1 2. 1 2 3 of 1 2 3 we get 1 3 2. 1 2 3 of 1 3 2 we get an identity element. Now 132 of identity element we get 132 itself. Then 132 of 1 2 we get 2 3. 132 of 1 3 we get 1 2. 132 of 2 3 we get 1 3. 132 of 1 2 3 we get identity element. 132 of 132 we get 1 2 3. So this is composition table. So these values are find in rough first, then write in composition table. So in composition table we observe that these all entries are from S3. So S3 is closed under composition. Now here we get identity element which is obtained from I of I, means I inverse is I. Here 1 2 of 1 2 we get identity element. So 1 2 inverse is 1 2. Here 1 3 of 1 3 we get identity element. So 1 3 inverse is 1 3 itself. Here 2 3 of 2 3 we get identity element. So 2 3 inverse is 2 3. Here we get 1 3 2 of 1 2 3 which is identity element. So 1 3 2 inverse is 1 2 3. Here we get 1 2 3 of 1 3 2 which is identity element. So 1 2 3 inverse is 1 3 2. Now we conclude from the composition table are as first property is closure property. So from the composition table we observe that composition is closed in S3. Now associative property. So we know that the composition of functions is associative and S3 is associative under composition. Now identity element. So we get I is 1 goes to 1, 2 goes to 2, 3 goes to 3 belongs to S3 is the identity element. Now existence of inverse. So we get I inverse is I, 1 2 inverse is 1 2, 1 3 inverse is 1 3, 2 3 inverse is 2 3. So these four elements are self-invertible elements. Now 1 2 3 inverse is 1 3 2 and 1 3 2 inverse is 1 2 3. Now commutative property. So from composition table we observe that S3 is not commutative under composition because 1 2 of 1 3 is 1 3 2 and 1 3 of 1 2 is 1 2 3. So these two elements are different. So S3 is not commutative under composition. So S3 is group but not commutative. So S3 with composition is non-abelian group. Thank you friends.